Hello everyone. Let's explore an essential concept in PySpark that plays a huge role in its efficiency and resource management lazy evaluation. Have you ever wondered why Spark doesn't process your transformations immediately? Understanding lazy evaluation will give you insight into how PySpark optimizes performance, minimizes resource use, and handles data efficiently. Introduction. Lazy evaluation is a fundamental concept in PySpark that influences how data transformations are processed. In PySpark, when you apply transformations like map, filter, or select, these operations are not executed immediately. Instead, Spark takes note of each transformation and builds an execution plan. This plan is organized as a series of operations in a directed acyclic graph or DAG, which records the dependencies between each transformation. Actual computation is delayed until an action like count, collect, or save is called on the data. At this point, Spark triggers the execution, evaluating the transformations in the most efficient order based on the DAG. This approach allows Spark to optimize the process, minimizing unnecessary data shuffling and reducing resource use by deferring computation. Spark ensures that it only processes data when absolutely needed, making it highly efficient for handling large-scale data tasks. How lazy evaluation works in PySpark. Transformation recording, when you apply transformations like map, filter, or select on an RDDD or data frame, PySpark doesn't process the data immediately. Instead, it records these operations in a directed acyclic graph tag. Each transformation is added as a node in the DAG, capturing the dependencies between steps and establishing an execution path. This recording process allows PySpark to build a list of planned operations without performing any actual computations yet. Execution plan creation. As transformations are applied, PySpark creates a logical plan that outlines how the data should be processed. Each transformation you apply adds to this logical plan without computing or altering the data itself. This plan serves as a blueprint for the final computation, ensuring that PySpark has a complete view of the operations before execution. This approach allows PySpark to gather all transformations and determine the most efficient path to execute them later. Triggering with actions. Execution is only triggered when an action such as collect, count, or show is invoked on the data. At this point, PySpark takes the logical plan and begins to perform the computations. Actions prompt PySpark to evaluate all previously recorded transformations in the DAG, executing them to generate the final output. This deferred approach means that no resources are consumed on computation until an action is explicitly called. Optimization. Before executing the DAG, PySpark applies an optimization process. Using the Catalyst optimizer for data frames, PySpark refines the execution plan to reduce data shuffling, combine compatible transformations, and manage memory usage efficiently. This optimization step helps to ensure that the computation is both fast and resource efficient, which is essential for handling large-scale data processing. The result is a streamlined execution that minimizes resource usage while maximizing performance. Why lazy evaluation is important. Optimize execution. Lazy evaluation enables Spark to optimize execution by deferring it until the entire directed cyclic graph tag of transformations is complete. With the full view of all transformations, Spark can streamline processing by combining multiple transformations and reducing data shuffling across nodes. This optimization minimizes computational costs, making the overall execution faster and more efficient. Fault tolerance. Lazy evaluation supports fault tolerance as operations are recorded rather than immediately executed. If there's a failure during execution, Spark can recover by recomputing any lost data from the DAC. This is especially valuable in distributed environments where node failures may occur, ensuring data processing continues without disruption. Reduce memory usage by deferring execution. Lazy evaluation helps Spark minimize memory usage. Intermediate results are not held in memory, as only the final required data is processed when an action is triggered. This approach is particularly memory efficient for large datasets, preventing unnecessary memory consumption and improving overall performance. Example of lazy evaluation in PySpark. In this example, we begin by creating a Spark session and defining a small sample dataset with names and salaries. This data is used to create a data frame in PySpark. The code then applies a series of transformations which illustrate PySpark's lazy evaluation in action. The first transformation filter filters out rows where the salary is less than or equal to 4,500, keeping only those rows where the salary is greater than 4,500. The second transformation, select, narrows down the data frame to just the name column, excluding the salary column. At this stage, however, no actual computation or data processing occurs. Instead, Spark records these transformations in a directed acyclic graph tag as part of its lazy evaluation strategy. Only when the action show is called on selected underscore df does PySpark trigger execution. This action instructs Spark to display the final results, prompting it to process all previously recorded transformations in the DAG. Spark then optimizes the execution plan and processes the data accordingly, returning the filtered and selected results. This lazy evaluation approach ensures that transformations are deferred until necessary, enabling Spark to optimize and efficiently manage memory and computational resources. Benefits of lazy evaluation. Improved performance. One of the primary benefits of lazy evaluation in PySpark is improved performance. By deferring execution until an action is called, Spark has a full view of all transformations applied to the data, allowing it to combine multiple transformations into a single optimized execution step. This optimization minimizes redundant computations, conserves resources, and results in faster processing overall. Data shuffling minimization. Lazy evaluation also allows Spark to minimize data shuffling, a costly operation in distributed computing that involves moving data across nodes in a cluster. By reorganizing transformations in the directed acyclic graph tag, Spark reduces unnecessary shuffles, which optimizes network bandwidth usage and shortens job execution times. This approach is essential for handling large datasets efficiently. Enhanced fault tolerance. Lazy evaluation enhances fault tolerance in Spark. Since the DAG records all transformations and dependencies, Spark can recompute any lost data in the event of a node failure. Rather than rerunning the entire job, Spark only reprocesses the affected portion of the data, leveraging the DAG to recover quickly and maintain data processing continuity in distributed environments. Common actions that trigger execution. Collect. The collect action retrieves all data from the dataset and brings it to the driver node. This action is useful when you need to analyze or manipulate the results locally on the driver, but it should be used with caution. For large datasets, collect can consume a significant amount of memory and may even cause memory overflow if the dataset is too large to fit into the driver's memory. Count. The count action calculates and returns the total number of elements in the dataset. This action is often used to quickly verify the size of the dataset after transformations, providing an efficient way to check how many records remain after filtering or other transformations. The show action displays the first few rows of the data frame directly in the console. This is especially useful for a quick preview of the data structure and content, helping you validate transformations before committing to further actions or saving the data. Save as text file. The save as text file action writes the dataset to storage as text files. This action is helpful for persisting results, allowing you to store processed data in a specific format for future access or external usage. It is commonly used to save outputs to a distributed file system like HDFS or local storage. For each, the for each action applies a specified function to each element in the dataset. It's a versatile action that enables custom operations on each record, executing all previous transformations in the process. This action is typically used for tasks like logging side effects or applying complex transformations on each individual element in the dataset. So that's lazy evaluation in PySpark. By deferring computation until an action is called, Spark can plan and optimize the workflow, making it more resource efficient and fault tolerant. This approach is what makes PySpark so powerful for big data processing, enabling it to handle complex transformations with ease. Keep lazy evaluation in mind as a key performance benefit in your PySpark projects. If you found this video helpful, please give it a thumbs up, subscribe for more PySpark content, and hit the notification bell to stay updated on our latest videos. Thanks for watching and see you in the next one.